All right, good morning. So our plan today is we're going to finish off chapter 19. I know it seems like it went fast, but there's not a whole lot of chapter 19 to do. It may have to get finished on Monday. We'll see how the hind end of this goes, but I think we should probably be able to get through most of it over the course of the next couple hours. Um, so what we learned the other day was we learned about the electric potential energy and the electric potential, right? The electric potential energy is a measure of how much energy it takes to put a set of charges in whatever location that set of charges is at. And for point charges, for a pair of point charges, we found that the potential energy looked like this. But of course, uh, we then went on to define something called the electric potential, and we defined the electric potential as the potential energy per charge, which means that for a point charge, we had that. Again, this is the electric potential energy. It's measured in joules. This is the electric potential. It's measured in volts. And the last thing we did the other day is we found that the electric field is related to the electric potential by this. And I want to talk a little bit before we move on about how to interpret this. Again, the thing that you should be looking at is that the electric field is given by the change in potential over the distance. So the idea is that if you have an electric potential that's changing from place to place to place, if you move in a certain direction and you find that the electric potential V has changed by a certain amount, the more that amount is, the larger the electric field. And this minus sign indicates that the electric field points in whatever direction the electric potential is getting smaller. So if I go from some place where V is 100 volts to some other place where V is 50 volts, that means that the electric field is pointing in the direction from the 100 to the 50. And in fact, since E is a vector, what will happen is you can get the components of E by moving in different directions. One of your homework problems utilizes this concept with a graph. Imagine I'm plotting V along a line in several locations. So this is as a function of X. And what I find is that V looks, I don't know, something like this. So maybe this is 10 volts. Maybe down here is 2 volts. Let's say that this point right here happens at, that's 0. Let's call that 2 meters. Let's call that 3 meters. Let's call that 5 meters. Let's call that 7 meters. And let's call the end of this graph 10 meters. So just looking at how V changes from place to place, I can actually figure out quite a lot about what the electric field is at different locations. How can I do that? Well, since the electric field is the change in potential over the distance, and if I'm looking at this graph, the change in potential is the rise of the graph, and the distance would be the change in x of the graph. What I'm looking at is a slope, right? And so if I look at the slope of what this function looks like, it will tell me what the electric field is doing. So for instance, if I look anywhere between 0 and 2, anywhere along this flat section of the graph, this has a slope of 0. But if the slope is 0, that implies there is no electric field in that region. Now, what about this region right here? Well, you can see that between 2 and 3, the potential drops from 10 volts down to 8 volt or to 2 volts. So it goes down by 8. So delta V during that section would be -8. The distance, meanwhile, 1 meter. So that implies that during this section here, the slope is -8/1 or -8. But since the electric field is the opposite of delta V over D, what that tells me is that since I have a negative slope here, my electric field is in the positive direction. So if I call left negative and right positive, here my electric field would be 8 newtons per coulomb, and it's to the right.
Dr. Fleming.
Yes, ma'am.
Okay, you said 1 meter somewhere?
Yeah, look. If I'm looking between here and here, how far did I go? I went from x equals 2 to x equals 3. That's 1 meter.
Oh, so you just, okay, never mind. I see what you did.
But remember, I'm doing the slope, so it's rise over run. So
Okay.
between here and here, the run was just 1.
Okay.
Yeah. Now, what about this section here? Well, this is another 0 slope. So here, I've got an electric field of 0 again. But then what about this section here? Between x equals 5 and x equals 7, I've got a positive slope again. How big is that positive slope? Well, the rise is from 2 up to 10, so that's a rise of 8. The run, however, is from 5 to 7. That's a run of 2. So 8/2 is 4. So right here, the electric field is 4 newtons per coulomb. However, because V is getting bigger, the slope is positive. That tells me that the electric field is in the negative direction. So here it's 4 newtons per coulomb, but it's in the opposite direction. It's to the left. And then, of course, back here, we're back to electric fields of 0. So by looking at how the electric potential changes in different locations, we can figure out what the electric field is. And a lot of times that's helpful to us because sometimes sitting down and calculating E is really a pain because it's a vector and it's got all these components. And so many times figuring out what the potential is easier than figuring out what the electric field is. And then once you know V, you can figure out what E is based on how V changes from place to place. So a lot of times that's our problem solving strategy is we'll figure out the potential and use it to find E rather than finding E directly because it might be more calculationally challenging. So this is all stuff that we sort of cracked last time. What I want to do next is we're going to introduce a new concept, and that's the concept of capacitance. And I want to revisit an example that we played with earlier because it's going to be helpful during this section. And that's the concept of the parallel plate capacitor.
Dr. Fleming.
Yes, sir.
It's just us two in this class?
There are 6 of you in total, but bear in mind it's an online class, so not everyone will be attending synchronously.
Got you. So basically, we both took this class already. Instead of us trying to teach us all the concepts and everything, can you just help us pass the class as far as like, can you help us?
So bear in mind that what we're doing right now is we're recording a video for everyone, including the people who aren't currently here.
Okay.
So I have to attend to everyone's needs. I got office hours. If you need one-on-one time, by all means, take use of those.
I bet. What time is your one-on-one time? You said 1:30 to 4:30. It's 1:30 to 4:30, right?
Something like that. I literally don't know. I'd have to look it up myself. No, I think it's 1 to 4. But that's why I put it in the syllabus.
All right, but you didn't specify the days. You said 4 days out the week. You never said the days.
The class meets 4 days a week.
Yeah, I understand, but you said office hours 4 days a week. If it's Monday through Thursday,
Yes,
then
those are the 4 days.
okay. All right, carry on.
All right. So moving on. We had this concept that we'd played with, this example we'd played with when we were drawing electric field lines, and that was the parallel plate capacitor. In a parallel plate capacitor, I've got two parallel plates, and what's going to happen is I'm going to load up one of those plates with a certain amount of positive charge. And the other plate, I'm going to load up with an equal amount of negative charge. So what we're looking at is the edges of these plates, but the plates are going to be separated by some distance that I'm going to call D. So D is just the size of the gap between those two parallel plates. And what we saw last time was that there was going to be an electric field in between those plates. Let's swap colors out real quick. And that electric field in the middle here was going to point straight from the positive plate to the negative plate. It was going to be a uniform electric field in that gap. And there was a field on the outside that was kind of curvy and complicated, but it was comparatively weak. And so we're going to mostly ignore that part of the field. It's not going to help us understand what's going on very well. All the action is going to happen here in this gap. Now, because we know that the electric field is related to the change in potential, remember E is equal to negative delta V over D. Because we know this, and because we know there's an electric field in this gap, that means that there's a difference in potential between one plate and the other plate. One plate will be at a higher potential than the other. Now, since E always points in the direction that V gets smaller, that says that this top plate is going to have a higher potential, and the bottom plate must be the lower potential. So we would say that there is a potential difference across the plates. That's the terminology we'll use when we talk about this. We're saying there's a high V here and a low V here, so there is a potential difference, delta V, across the plates. Now, what's going to happen is the more charge we put on these plates, the bigger the electric field would be, right? If there's more charge, there's going to be a bigger electric field. But if there's a bigger electric field, there'd be a bigger potential difference. So there's going to be a relationship between the size of the potential difference that we put on it and the amount of charge we have to put on those plates. And that is where this concept of capacitance is going to come in. What we're going to do is we're going to say that the capacitance, which we're going to denote with the letter C, we're going to define it as the ratio of how much charge we've got to put on those plates to the size of the potential difference, the voltage difference from one plate to the other that's required. Now, why might we care about that? Well, imagine that I hook these two plates up to, let's say, a 10-volt battery. A 10-volt battery is going to push a certain amount of charge onto those plates. If I were to then swap it out for a Duracell 1.5-volt battery, that 1.5-volt battery can't push out as much charge. It's weaker. I would get less charge on those plates. So the behavior of the charges on the plates will depend on what voltage I drive onto them. It's going to tell me how hard I have to work to charge those up. And what's going to happen is capacitors are going to end up fulfilling a function in a lot of circuits. Sometimes capacitors are useful as a means of storing charge and saving energy up to be used later, not unlike a battery. Other times, capacitors are going to be useful for looking at the rate at which you can put charge on them. Sometimes it takes a certain amount of time to charge them up or to discharge them back down. And by utilizing the fact that it takes a reliable amount of time to do either of those things, we can make things like timer circuits. The little intermittent windshield washers that you have in your car, those are driven by a capacitor circuit. And when you go from the low setting where the wipers go back and forth very intermittently to the high setting where the wipers go back and forth almost constantly, what you're essentially doing is you're changing the properties of a capacitor in that circuit to allow it to behave differently in your car. So this is our definition of capacitance. The units of capacitance would be coulombs per volt. And we're going to give that a name. A coulomb per volt. It's called a farad. And that'll be our SI unit of capacitance. Now, I should warn you in advance that a farad is a huge unit, and you will almost never see a 1 farad capacitor anywhere. It's very difficult to create one. And so as a consequence, you should probably get used to seeing much, much smaller units. Microfarads will not be uncommon, but even nano or picofarads would often be something you'll run into. So be prepared for that. But remember, the SI unit is the farad, and you're going to want to probably convert from nano or micro or picofarads into farads, and that means you need to be familiar with those metric prefixes. All right, so far so good. I apologize, my allergies are going berserk this morning. I can barely breathe. All right, so let's figure out how this capacitance gets determined. And in order for me to see that, I'm going to have to utilize a couple of things that we already know. One is that we know the potential difference is related to the electric field. And since I don't really care about the direction of E, I'm going to just suppress that minus sign. The direction is all we care about, so we're looking for a magnitude. And for a parallel plate capacitor, I could just swap out that delta V with, if I just rearrange this, again, I'm dropping the minus sign because I only care about the magnitude, not the direction. But the potential difference would be equal to the electric field times the size of that gap. Now, something that you don't know, and I can't derive for you without doing a little bit of calculus, is how the electric field is related to Q. But it turns out that the electric field in between those capacitor plates is given by something called sigma, the charge density, over epsilon naught. Now, what the heck does charge density mean? Well, a density is always about how closely packed something is. And in the case of these plates, the charge is packed on a two-dimensional plate. So this charge density would be the total charge on the plate divided by the area of the plate. Now, what the heck is this epsilon naught? Well, in a way, we sort of already know it. We've seen it in a different form. If you recall, all of our point charge equations had this Coulomb constant K. And K was equal to a really big number, 8.99 times 10 to the 9th Newton meters squared per Coulomb squared. But it turns out that K is related to this constant right here. And that K is equal to 1 over 4 pi times this constant epsilon naught. And epsilon naught itself has a name. It is called the permittivity of free space. Now, what the heck does permittivity even mean? It doesn't matter. The name was kind of created back in the 1800s when we didn't really know what was going on. And so it was part of a theory that we've long since discarded. And unfortunately, the name has stuck. So it kind of doesn't mean anything. And it's just a constant that is related to the nature of the electric field. We're going to see it again in some of these subsequent chapters. Now, if K is 8.99 times 10 to the ninth, and it's equal to 1 over 4 pi epsilon naught, since this is such a huge number, the only way to get a huge number by dividing by something is to divide by a tiny number. So epsilon naught is going to be a super tiny number. And in fact, when you work it out, epsilon naught ends up being about 8.85 times 10 to the negative 12th coulombs squared per Newton meter squared. It is an entirely tiny little number. So if I take this and I pop that in there and replace E, look what happens. I've got Q over Q A epsilon naught D. When you divide a fraction by a fraction, it's the same as multiplying by the reciprocal. So what's going to happen is this is going to get shifted up to the numerator, and this Q and this Q here will cancel. So you end up with epsilon naught times A divided by D. This is the capacitance of a parallel plate capacitor. And what I want you to take away from that is that the capacitance depends only on the size and the shape of the capacitor, right? If the distance between the two plates gets large, if the plates are far apart, I'm dividing by a bigger number, my capacitance is going to be smaller. So making this gap get bigger reduces my capacitance. By the same token, if I take the area of the plates, if I make the plates themselves larger, then I can fit more charge onto them. And I'll get more charge per volt of battery because I can spread the charge out more. So larger area tends to increase the capacitance. So as long as you know the size and the shape of a capacitor, you know the capacitance. And the capacitance will never depend on things like what battery I hook it up to or what charge I put on it. That doesn't make a difference. The capacitance is a property only of the geometry of the capacitor. Nifty. Now, we can make it a little bit more complicated, and I can make it more complicated by realizing that in this little gap here, I've got a tiny amount of space. Oftentimes, the spacing on those capacitor plates is going to end up being like a fraction of a millimeter. They're often incredibly tiny. But I've got a bunch of positive charge and a bunch of negative charge and a super tiny little gap between them. And this positive plate is going to be attracted to that negative plate. They're trying to slap together. I don't want that to happen, right? If the two plates touch each other, the positive charge and the negative charge would cancel each other out. So what I have to do is I have to build the capacitor by finding some way of keeping these two plates from touching each other. And that's really hard to do if I don't put something in the middle to keep them separated. So most capacitors, just for practical reasons, are going to end up having some material in between the plates that keeps the two plates separated. However, it's got to be a material that is a non-conductor. In other words, if I had something like a piece of metal in between them, well, charge can flow very easily through that piece of metal. And so if I had a conductor that charge could flow through, then what would happen is if I put that in the middle, the positive charges would just flow right through the thing in the middle, get to the negative charges and cancel them out. I don't want that. So what I have to do is put in something that is a non-conductor, something that charge cannot flow through, something like rubber or glass. That material will keep the charges separate, and it won't let the charge leak through the gap. The term we use for that is dielectric. But a dielectric is just a fancy schmancy term for a non-conductor. And so most capacitors are going to have a dielectric in that gap. So I'll have the positive plate, the negative plate, and in between I've got some kind of material that keeps them separate. But here's the issue. I can't just have an electric field and not have it affect the material in the middle, because the material in the middle is made of atoms, and atoms are made of charge. And so what's going to happen is when I activate this capacitor in the presence of that dielectric, it's going to behave differently than it would if there was nothing in between. To see how that is, let me pull back the simulation we took a look at the other day. What I need it did not load properly. There we go. I need that stupid balloon sim. There we go. So we looked at this the other day when we were talking about conservation of charge. So here's a sweater, and right now we're showing all the charges in all the objects. So I have a sweater where there's a bunch of positive charges and negative charges, a balloon where there's some positive charges and negative charges, and here's a wall that also has a bunch of positive and negative charges. And right now, everything is electrically neutral, because for every bit of positive charge, I have some negative charge. However, if I take this balloon and I rub the sweater with it, what can happen is I can end up removing some charge from the sweater and adding them to the balloon. And so what's going to happen is now the sweater, which used to be electrically neutral, now it has more positive charge than negative charge. So it has acquired a certain amount of positive charge. And the balloon, which also used to be electrically neutral, it's ended up acquiring a certain amount of extra negative charge. So if I look at just the charge differences, what I can see is that the sweater has acquired positive charge, the balloon has acquired negative charge, and as a consequence, those two things are attracted to each other, right? That's not super surprising. What might be surprising is if I take the balloon and I move it close to the wall, the balloon gets stuck to the wall as well. But as you can see, the wall has a net charge of 0. There is no net charge on the wall. So why are my negative charges being attracted to a neutral wall? If the Coulomb force is K Q1 Q2 over R squared, and the balloon has Q1 of negative something, and the wall has a Q2 of 0, you would expect the force to be 0. And the reason that you don't see that is because if I show you all the charges, watch what happens to the wall as I bring the balloon closer. So here's my balloon that's got a whole bunch of extra negative charge. And as the balloon gets closer, you see those negatives? Can you see them moving? Now, what's happened is the charge on the wall hasn't changed at all, But what has happened is as I bring these negative charges close, the negative charges in the wall right here, they're getting pushed a little bit away because they're being repelled from all of these negative charges. Now, what's happening inside that material? Well, all the atoms in the wall are composed of positive nuclei surrounded by a cloud of negative electrons. And that electron cloud, when you bring the balloon close, all the electrons get pushed away, and that cloud can kind of deform and move itself around a little bit. The electrons are still stuck on the atom, so like this electron right here is still stuck on this atom. It can't quite get away, but it is being pushed further apart. It's changing the shape of that orbital on that particular atom. And as a consequence, what happens is the positive part of that atom is a little bit closer to the balloon than the negative part of that atom. The negative part got pushed a little bit further away. And that means the attraction between these negative charges and the positive part of this atom is a little bit larger than the repulsion of the negative balloon and this negative bit of charge. When I take the balloon away, it goes back to normal. But as I bring it close, it's pushing the electrons around by changing the shape of the atom. Right. This process is called polarization. And in my capacitor, if I put a dielectric in there, I expect that I should get some amount of polarization inside my material. So what that means is that if this material consists of a bunch of atoms, so mention these are individual atoms inside my material, what's going to happen is the negative parts of the atoms are going to get pulled a little bit closer to the plus side of my capacitor. So this will be a little bit more negative. The positive parts of the atoms are going to get pulled a little bit more toward the negative plate. So each atom is going to acquire a small dipole moment. And when that happens, it's going to generate an electric field. But look, the electric field created by each of these atoms is from the positive to the negative. It's upward. But the electric field created by the plates, I was using red earlier, is the opposite direction. So what's going to happen is the electric field in this gap is going to have the regular electric field that you would have had if there was no dielectric, minus this tiny little electric field created by the polarization. And so it means the size of the electric field inside those plates is going to be a little bit smaller than it otherwise would have been. But since the capacitance is Q over delta V, I have the same amount of charge on the plates as I used to, but since E times D equals delta V, since E is smaller than it used to be, delta V is smaller than it used to be. So I'm going to have the same Q as before, but a smaller delta V. I've got a bigger capacitance. So by putting a dielectric in that gap, I'm going to make the capacitance bigger than the normal capacitance. Now, the normal capacitance was this. Putting a dielectric in the middle is going to make it bigger than this. And to see how much bigger it is, we're going to invent a new concept. And it's called the dielectric constant. This is going to look like a letter K, but it's not. It's a scripty K. It's the Greek letter kappa. And this is what we're going to call the dielectric constant. Now, the dielectric constant is going to be a measure of how easy it is to distort the shape of an atom or a molecule. So when I distort the shape of these atoms and create this tiny little dipole inside the atoms, it's going to depend on how easy it is to distort the shape of that atom. Some are not going to distort very much at all. So the size of this effect will be small. Other atoms are going to very, very easily separate into a positive side and a negative side. Some of the materials might have had a dipole moment to begin with. So they're going to be super, super responsive. Think like when you guys learned about polar molecules back in general chemistry. Some molecules are by their nature polar. Water is an example, right? Water has one oxygen and two hydrogens, but the oxygen hogs all the electrons. So the oxygen side of any water molecule is a little bit negative, and the hydrogen side of every water molecule is a little bit positive. So if you had water molecules in here, what would happen is all your water molecules would have a tendency to want to line up so that the oxygen side of the molecule is closer to the top of the plate, and the hydrogen side would be closer to the bottom side of the plate. So water molecules would be very susceptible to this effect. Now, this dielectric constant is going to be different for every different kind of material. However, we're going to define kappa as the ratio of the electric field we would have gotten if there was no dielectric in the middle, divided by the electric field that we actually get. And notice what's going to happen is, since this dielectric constant effect always tends to make the electric field smaller, this we always expect to be smaller than this. What that means is that this number, at best, if this didn't happen at all, then these two things would be the same, and the dielectric constant would be equal to 1. But if this happens even a little bit, the dielectric constant is going to be larger than 1. So kappa starts at 1, but can always be bigger for any material. By definition, the kappa of vacuum is 1. So if I have nothing in between the plates, we say that that's equal to 1. If I have air, nothing but just air in between the plates, air doesn't polarize very much. And in reality, it's like 1.0024 or something, but we usually call that 1. So the only dielectric constant that I require you guys to know off the top of your head is that for vacuum or air, the dielectric constant is equal to 1. For any other material, it will be larger than 1. And there's a chart in your textbook that lists the dielectric constant of lots of different materials. I think that like a piece of paper is a non-conductor. It has a dielectric constant of about 2 or 3. Deionized water has a dielectric constant of about 80. There are some ceramics that are often used in capacitors that have dielectric constants of 2 to 300. Now, how does this affect the value of C? Well, it turns out that what's going to happen is, because if I rearrange this, because kappa is going to play the role of a multiplier effect, it's going to play a role of a multiplier effect here as well. And in fact, all we have to do is just multiply by kappa. So if I have air or vacuum in between, kappa is equal to 1, and we just have the same expression we had a minute ago. If I have any other kind of material, kappa is greater than 1, and my capacitance is going to be a little bit extra large. So this is our corrected expression for the capacitance of a parallel plate capacitor, but adding in the effect of the dielectric in between. So far, so good. So once we have that under our belts, We understand the concept of the dielectric, or the capacitance. We've got a handle on sort of what to expect from it. Obviously, we're going to make it more complicated. The place we're going to go next is we're going to allow ourselves to have more than a single capacitor once. So, what happens if I have more than one capacitor at a time? So, let's imagine a scenario. Gross. I'm going to have a capacitor, and we're going to draw a lot of circuit diagrams in this course. And so we probably should get familiar with the symbology of a circuit diagram. So here's what we've got. I'm going to have a parallel plate capacitor. And in circuit diagrams, anytime you want to draw a capacitor, you'll draw two lines that are of equal length right next to each other. That's obviously the symbol for a capacitor. Then I'm going to have it connected by wires, which I'll denote with little lines. Now I'm going to hook this capacitor up to a battery. And we haven't talked about batteries in this course. So let's think about what batteries are. So the symbol for batteries in a schematic diagram like this is two parallel lines of unequal length. So I'll have one long line and one short line. And conceptually, when you think about like batteries, you usually think about like your Duracell AA batteries. And so your AA batteries always have a plus side and a minus side. The plus side is the side with the little indentation coming out of it. And the minus side is the side that's flat. So when you see this symbol in a circuit diagram, this longer line is just this side of the battery. This shorter line is just this side of the battery. That's the way to think about it. Now, what the heck is a battery actually doing? How do batteries work? Well, I've taken versions of this class several times in my life. I took, obviously, my freshman year, I took this course. But then as a senior, if you're a physics major, you have to take a 2-semester electricity and magnetism class, which is like this class on steroids. Then in graduate school, I took another 2-semester course, which was, that class on extra steroids. It was the hardest class I've ever taken in my life. It sucked. And the professor that I had for the latter of those, the graduate level of this course, when talking about batteries, here's how he explained them. So obviously this was a graduate level E&M class. What he's saying absolutely must be true. Here's how batteries work. Inside every battery, there lives a little elf. And what this elf's job is to reach down at the atoms at his feet and to grab positive charge from his feet and stick them up by his head. So every time he grabs a little piece of positive charge down here, he's going to leave behind a bit of negative charge and put a bunch of positive charge on the top. Put more negatives, positives, negatives, positives, negatives, positives. That's what he does all day long. He just reaches down, grabs negative charge or positive charge from his feet, and sticks it up there by his head. Now, obviously, these charges, they want to attract one another, so these charges want to come down here and cancel those out, but the elf, he won't let them. He keeps those two charges separated by a certain distance. And as a consequence, he'll generate a potential difference from one side of the battery to the other. So if it was a Duracell battery, what's going to happen is the potential difference across that might be For a Duracell, it's like 1.5 volts. If it was a 12-volt battery, it would be 12. You know, it's whatever the particular potential of that battery is. The ELF's job is to keep charges separated until that potential is equal to whatever that value is. He wants to keep that voltage constant at all costs. Now, if I take that battery and I hook it up to a circuit, what I'm essentially doing is I'm providing wires that allow a path for the charges at the top of that battery to go through that path to cancel out those negative charges. Now, if the ELF weren't doing anything, these positive charges would just flow through this path, cancel out all those negatives, and the charges would cancel out. And if they did, the potential difference across the battery would drop to 0. However, every time one of these positive charges slips away and tries to cancel out one of those negative charges, the ELF is just too fast. He reaches down immediately, grabs it, sticks it back up. So as these charges flow through and try to cancel each other out, the ELF is constantly replacing those charges. And he keeps doing that so that the potential difference always stays constant at 1.5 volts. That's what's happening. Now, what could happen, if I let the charge flow out of here too quickly, there's a limit to how fast the ELF can work. And if I let too much charge come out at once, the ELF can't keep up, and the amount of charge accumulated at either pole of this battery would start to drop down. So normally we say this voltage would be constant, but in practice, if the faster you pull charge out, the more that will drop. This is what we call like the case of an ideal battery versus a non-ideal battery. In a perfect world, the ELF could always keep up. That voltage will always be constant at 1.5. But in a practical sense, sometimes it'll be a little bit less than 1.5 because the ELF gets a little bit behind. We're going to assume in this class almost always that our batteries are ideal batteries, and we're going to ignore the fact that our ELF can't usually keep up and pretend like he totally can. It makes our lives simpler. There may be a problem on the homework where you consider what happens if he can't, but I don't recall. So that's what's happening. And that's how our battery is going to work. So what's going to happen is when I hook this battery up to this capacitor, positive charge is going to flow out of here, trying to go through. That positive charge will accumulate on the top of that capacitor plate, but this positive charge will drive positive charges away from here. Those positive charges will go over here and try to cancel out the bottom terminal of the battery, and the ELF will just replace them. But they'll leave behind negative charge. So what's going to happen is when I hook this battery up to that capacitor, I will accumulate charge on the capacitor, and I'm going to keep accumulating charge until the voltage difference across the capacitor is the same as the voltage of my battery. So if this is a 1.5 volt battery, I'll end up with 1.5 volts across my capacitor by the time everything's all said and done. Now, obviously, what I've told you about elves is probably not true. I know you're shocked to think that I might lie, and you were so queued up to believe little fairies live inside every battery, but it's not really an elf. It's not really a fairy. It's actually a chemical reaction. And what's really happening, right, is you've got one material at one pole, you've got a different material at another pole, and in between you've got some kind of acid usually. And what's happening is there's a chemical reaction happening at one pole, and the chemical reaction at that pole requires extra charge in order to happen. So what's going to happen is you've got, you know, the metal, whatever the metal is, plus the acid, plus electrons yields stuff. That's the chemical reaction that's happening at one terminal. And it depends on what the metal is, what the acid is, what kind of battery you've got. I don't especially care because this is not a chemistry class. Down here, what's going to happen is you've got a similar reaction, but this reaction tends to produce extra electrons. So here you've got metal plus acid yields stuff plus free electrons. So what's going to happen is these two chemical reactions are occurring, and you end up reaching chemical equilibrium. And when you do, you end up with a certain deficit of negative charges at this terminal because I'm using up negative charges. That's why it becomes positively charged. Down here, I end up with a surfeit of negative charges because as this reaction occurs, it's spitting out extra electrons, and I don't have anywhere to put them. So that becomes negatively charged. And the size of the voltage is going to depend on the energetics of whatever that chemical reaction is. That's why it's 1.5 volts, is because that's the energy difference of those two chemical reactions. So yay, whatever. Why can the ELF not always keep up? Because chemical reactions have certain reaction rates. And so this reaction can only happen so fast. Normally what happens is as you pull charge out, you are throwing this chemical reaction out of chemical equilibrium. You pull away some negative charges, and now I've got more space to produce more or to use more. So that's what's happening. And if you pull it out too fast, the chemical reaction can't keep up and the voltage will drop. But if you give the time for the products to reestablish themselves, you'll get back into equilibrium. So in reality, that's what's happening. But the point that my professor was making with the stupid ELF story is that we don't especially care what the chemistry is. All we care is stuff is happening in the battery. It's producing a voltage difference, and that voltage difference is basically constant. That's the idea. So as far as we're concerned, it might as well be ELVs because we're not going to worry about the chemical reaction. That's beyond the scope of what we're dealing with. So I hook one of these guys up, and what's going to happen is I'll get charge accumulated on the capacitor, and it will produce a potential difference equal to that of the battery. Yay, super easy. But what would happen if I had more than one capacitor? What if I had a battery but I connected two separate capacitors? Now, what's going to happen is I'll call this over here V total. That's the potential difference across the battery. And I'll call this capacitor 1, capacitor 2. Now, what's going to happen is there's no electric field inside this wire. So the potential difference from, say, here to here or here to here, anywhere along here, V should not be changing. V is only going to change when I have an electric field. And I'm going to have an electric field inside the gaps between those two plates. So the potential here and the potential here should be slightly different. I'll call that delta V1. That's the voltage drop across that first capacitor. By the same reasoning, V should be the same here as it is here, but it will change from here to here. I'll call that delta V2. Now, there's charge on those plates. Where did the charge come from? Well, when I hooked the battery up, charge flew out, so I had positive charge flowing out. It accumulated on the top capacitor. It drove positive charge away from the bottom part of that capacitor. But where did that positive charge go? It went here. And that, of course, drove away positive charge from there, leaving behind negatives. But what's going to happen is all the charge that appears on that second capacitor, it came from the bottom plate of the first capacitor. So I can't get charge on this unless I pulled it from there. That tells me that in this configuration, the charge on that first capacitor, which I'll call Q1, has to be the same as the charge on the second capacitor. So Q1 has to be the same as Q2 because there's no way to get the charge onto the second capacitor without coming from the first capacitor. What's more, where did the charge on the first capacitor come from? It's the charge that came out of the battery. I'll call the charge coming out of that Q total. And according to this, Q total should be the same as Q1, which should be the same as Q2. So whatever charge comes out of the battery has to be the same as the amount of charge on either of the two capacitors. They both have to have the same amount of charge. Nifty. Now, what about the electric potential? Well, I know that because the ELF is doing his job, the potential difference from here to here has to be some number, whatever V total is. So just for conversation's sake, let's assume that V total is 10 volts. So from here to here is 10 volts. So maybe this is 0 volts. This up here is 10 volts. But if I move from here where it's 10 volts to here, there shouldn't be a change because there's no electric field. So if this is 10 volts, that's also 10 volts. This is also 10 volts. It's 10 volts everywhere along here. Same reasoning. If this is 0 volts, it's 0 volts here, 0 volts here, 0 volts here, because there can't be any change in between. However, if this is 10 volts here, it's got to be something other than 10 volts right here because there's a difference of delta V1 right there. So here it's going to go from 10 volts down to something less than 10 volts. I'm not really sure how much less, but definitely less. When I go from here to here, it's going to drop again. Oh, but we already said right here it was 0, right? So this drop and this drop better add up to 10. Otherwise, this can't be right. So the conclusion we have to draw from that is that whatever the voltage of my battery is, delta V total, it's got to equal the voltage drop across the first capacitor plus the voltage drop across the second capacitor. I can add those two voltages together. They will have to add up to the full, say, 10. Now, they don't have to be equal. It doesn't have to be 5 volts plus 5 volts. It could be 9 volts for the first one and 1 volt for the second one, or 8 volts for the first one and 2 volts for the second one. Any combination that adds up to 10 would technically work. It's going to depend on how big those capacitors are, as we'll see here in a minute. But that's the idea. So I've got these two rules that we've established. And what I want to do is I want to imagine that, when I hook these two capacitors together and I hook them up to that battery, a certain amount of charge comes out of that capacitor. But I can always imagine taking that same battery, hooking it up to a single capacitor, and having this single capacitor pull the same amount of charge out of the battery as these guys do together. In other words, we're saying that this hypothetical capacitance is equivalent to this capacitance. And oftentimes, what we'll do in problems is we will figure out what the equivalent capacitance is of some combination of capacitors. I'd like to figure that out. Now, what's going to happen is I've got these two rules, and I also know that the definition of capacitance has to be true for every capacitor ever. The definition of capacitance is that C equals Q over delta V. So taking these three rules and putting them all together, I should be able to figure out how big this equivalent capacitance is compared to my actual capacitance. Here's how it's going to work. If this is true for every capacitor, it's got to be true for this. I have to be able to say that C total ought to equal Q total over V total, where V total is this voltage, Q total is the charge on this hypothetical capacitor. But this also has to be true for each individual capacitor. So I should be able to say that C1 should equal Q1 over delta V1, and C2 ought to equal Q2 over delta V2. Cool. Now, if I take these expressions and I rearrange them, I can solve them for V. So for instance, if I solve this for V, I would get that V total has to equal Q total divided by C total. And by the same logic, I can do the same thing with V1, right? Delta V1 should equal Q1 over C1, and delta V2 is Q2 over C2. I just took these and rearranged them to get that. But then I can replace delta V total with this, delta V1 with this, delta V2 with this. So this expression is going to turn into Q total over C total equals Q1 over C1 plus Q2 over C2. However, we set up here that Q1, Q2, and Q total are all the same, which means all of these are the same, which means they all cancel. If they cancel, it's going to leave behind 1 over C total equals 1 over C1 plus 1 over C2. So this tells me how the equivalent capacitance is related to my individual capacitors. This is my equivalent capacitance rule. However, these two capacitors are connected in a particular way. Any charge coming out of the battery has to go through both of them or none of them. We say that they are connected in series. So this is the rule for capacitors in series. Again, how do I know two things are in series? If they are in series, anything going through one has no choice but to also go through the other. So this is my equivalent capacitance rule. Notice I did this for two capacitors. If I had added a third capacitor, all that would have happened was I would have had an extra term. And I can keep doing that forever. So you can probably guess what's going to happen next. What if I have capacitors that aren't in series? What if I do this instead? Here's my battery. Here's capacitor 1. Here's capacitor 2. Well, now let's think about what's going to happen. I have charge leave this battery. So little electrons are coming out of this battery. They get right here. There's a place where there's a choice. The electrons could travel this way, or they could travel this way instead. What that means is that the charge that ends up on this capacitor doesn't actually have to end up on that capacitor. The charge that comes over here doesn't have to go through there. So in this scenario, the two charges don't have to be the same like they were before. However, what is true is that everything that comes out of the battery has to go one of two paths. It either goes this way or this way. So I could say that Q total should equal Q1 plus Q2. This is basically a statement of conservation of charge, saying that all the charge coming out of the battery has to end up on either of the two capacitors. Pretty nifty. What about the voltage? Imagine this is 10 volts, and there's no change wherever there's no electric field. So this is 10 volts, that's 10 volts, 10 volts, 10 volts. It's going to drop, except now it can't change until it gets back to the battery. So from here to here is 10 volts, from here to here is 10 volts. So that tells me that delta V total has to equal delta V1. And by the same reasoning, delta V2 as well. So when I connect my capacitors in this fashion, the voltage drops across all of them have to be the same. That's different from before. We say that these are connected in parallel. How do I know that two things are in parallel? In parallel means that I either go through one or the other, but never both. So what would the rule then be if I have these guys and I want to imagine them being replaced by a single capacitor that pulls the same amount of charge out of the battery? Well, I'll do the same trick we did before. I know that since C total equals Q total over V total, that's got to be true. But here, the thing that I'm adding up are Q's, not V's. Let's solve this for Q. This implies that Q total equals C total times V total. And by the same reasoning, Q1 would equal C1 times V1, and Q2 would equal C2 times V2. So I could take this expression, replace Q total with C total delta V total. Replace Q1 with C1 delta V1. Replace Q2 with C2 delta V2. Except, wait a second, all the V's were the same, right? Which means they cancel. So C total would equal C1 plus C2. So apparently when you put them in parallel, you can just add the capacitances up. They'll act like a capacitor that's that much bigger. And of course, if there was a third one, I would just keep going. So that's my equivalent capacitance. In parallel. Super easy. So, obviously, you know what's going to happen next. We're going to make it more complicated. And this is probably where things are going to start to get a little bit tough. What if I make it way more complicated? What if I just load myself up with a ton, just a positive ton of capacitances? Here's a battery, here's a capacitor, here's a capacitor, heck, here's a capacitor, here's a capacitor. I'm just going to go nuts. All right. So I'll call you C1, C2, C3, C4, and C5. And you're, of course, V total. I want to find the total capacitance of all of these guys together. And let's go ahead and say that C1 is equal to 100 microfarads. C2 is equal to 150 microfarads. C3 is equal to 200 microfarads. C4 is 250 microfarads. And C5, 300 microfarads. So I'm going to start combining all of these things into one big capacitor. But the problem is I have to be able to identify which ones are in series and which ones are in parallel. And that's sometimes not super obvious. So the thing that I'll tell you is that when you're trying to identify these things, you want to remember that the definition of being in series and being in parallel. Two things will be in series if I can make the statement that any charge that goes through one has to go through the other one. There can't be any choices in the matter. And I can say that two things are in parallel if I can make the statement that any charge that goes through one either goes through one or the other, but never both. And sometimes that's confusing to students because what some students do is they erroneously look at something like this and they say, oh, these are in parallel, And in their minds, they think parallel means they're side by side. That will get you in trouble. Don't think that. That doesn't work. Because if you thought that, you might think, oh, look, these are side by side. They must be in parallel. But as we're going to see by the end, they're not. They also think that series means one after the other. So they're like, oh, this comes right after this, so these are in series. That's also incorrect. Right? The way that I know that it's incorrect is because if I have charge coming through C1, it could go through C3, but it doesn't have to. To be in series, I have to be able to say anything going through one must go through the other. And I don't have to go through C3 just because I went through C1. So these guys here are not in series. These guys here are not in parallel because to be in parallel, you got to go through one or the other, but not both. Here, I could go through this, then this, and eventually go through this. So the charge that goes through this will eventually go through this. They're not in parallel.
C4 and C5 are in series.
That is absolutely correct. So what we'll do is we'll look for things we can reduce down, and C4 and C5 is a really good place to start. Because if I get right here, it doesn't matter who I went through before. If I get to be right here, once I commit to this spot here, I got to go through both of them. So they're definitely in series. So what I would do if I was reducing this down to the equivalent capacitance is I would break this problem up into a bunch of little tiny mini problems. And the first thing I would do is to combine these guys and turn that into one big capacitor. Since they're in series with each other, I'll use the series rule, which says that 1 over C, I'll call it C4, 5, because it's 4 and 5 combined, should equal 1 over C4 plus 1 over C5. Well, that's 1 over 250 plus 1 over 300. And so a lot of times I'll find a common denominator, but this one's probably not super easy. So 250 plus.
I got 0.0073.
Except that's not C total.
I know.
Right?
Then you take the inverse of that, right?
Yeah. So
okay.
That's not C total. It's 1 over C total. So I got to take the reciprocal of that, which is 136. So I can imagine that these guys here are replaced by 136 microfarads. But now if I treat this as like one big 136 microfarad capacitor, I got to combine stuff down even further. Well, the thing that I notice is that if I get to be right here, I have a choice. I can either go this way, or I could go through this big 136 capacitor, but either way, I end up in the same spot. So this is in parallel with both of these. So if I add this plus this, so now I've got this as a single big capacitor. The rule for things in parallel is just add them. So C3, 4, 5 combined is just going to be C3 plus C4, 5. C3 is 200, so it's going to be 336.36 microfarads. So now I'm going to treat everything in that box as one really big capacitor. So now I go through this, then through this, then through this. So this, and this are all in series. So now I'll use the series rule one last time. So 1 over C total for the whole problem is going to be 1 over C1 plus 1 over C3, 4, 5 combined, plus 1 over C2. So 100 plus 50 plus. So together, that's 0.1096, we'll call it. And when I take the reciprocal of that, I get 9. I'm double checking that because that seems wrong. I expect it to be smaller, but that's a little surprisingly small.
Dr. Mom, I got something else.
That's why I'm double checking. I may have made a typo, but I am very suspicious of that. Apparently I got dyslexic. That's where I went wrong. This is not 1.096, it's 0.0196.
Oh, okay. Yeah, that's what I got.
Okay. Yeah. Which means my answer is not 9, but 50.9. Yeah. It makes a difference when you write numbers down in the wrong order. Go figure. So that's how you do this. And no matter how complicated a problem I throw at you, you can always break them down just by breaking them down into little tiny pieces. All right, super easy.
Mm-hmm.
Okay. Now, a lot of times what's going to happen is we're going to need to know, like, not just what the equivalent capacitance is, we're also going to have to know, like, how much charge ends up on each capacitor. And that's a problem that requires a few more additional steps. So since we've already done like half the work here, let's take this particular set of capacitors and let's assume that the battery I'm hooking them up to is a 12-volt battery. And what I want to do now is figure out how much charge is going to end up on each of these 5 capacitors. Now, anytime you're doing a problem like this, the first step of that problem is going to be to find the total capacitance, which we've already done, right? So what remains is to figure out how the charge coming out of the battery gets split up amongst all these things. So when doing a problem like this, and I want to find how much charge is on each individual capacitor, step 1 is find C total, which we did. Right? Now, once we know what C total is, we're going to find Q total. How much charge came out of that battery? Now, conveniently, we know that C total equals Q total over V total. This we figured out. This was given in the problem. This we can therefore determine. Q total should equal C total times V total. So we know that C total was 50.9 microfarads. V total we said was 12. So the total charge coming out of the battery is going to be about 6.1 times 10 to the negative 4 coulombs. So that's what's coming out of that battery. We know what's coming out of the battery. So once we know Q total, we're then going to look back at our circuit and ask ourselves, are there any capacitors for which I can say that you can't come out of the battery without going through that capacitor? If that's the case, the capacitors for which that is true will have to have Q total on them. So, it's back at my original circuit. Here's my battery, and I have this much charge coming out of this battery. Now, what's going to happen is it's going to come out here. I'm going to get to capacitor 1, and there's no way to come out of the battery without going through capacitor 1. That tells me that capacitor 1 has to have the full Q total charge on it. So I already know that Q1 has to equal this. Now Q2, Q3, Q4, Q5, those all may be different. But I know that everything that coming out of the battery has to go through capacitor 1. Now, I get to this little intersection. Some of that Q total is going to go this way. Some is going to go this way. So these three are going to have less charge than Q total. I'm not sure how much less yet, but they're going to have less. However, all the charge eventually meets back up here, and it has to go through Q2 to get back to the battery. So in this case here, C2 will also have the same amount of charge as C1. So this, for this particular problem, has to be the same. So far, so good. So now what's going to happen is we're going to start filling in blanks, because from here on out, what's going to happen is we can use a combination of the definition of the capacitance as well as charge conservation, and what we call the loop rule to fill in blanks. So charge conservation is going to be what we're eventually going to start calling the junction rule. But basically what it says is that all the charge has to go someplace. So for instance, if I know how much charge comes into this intersection, well, all the charge coming out has to add up to the charge coming in, right? None of the charge is going to hit this intersection and vanish. It's all got to be accounted for. That's a rule. The loop rule says that all the voltages have to add up to V total, right? We saw that here and here. If I went around a loop, all these V's added up to V total. That's going to be true no matter how complicated the circuit gets. So, for instance, if I go around this loop here, if this is 12 volts, I'm going to drop V1 across this, V3 across this, and V2 across this, but I've got to get back to 0. So that means this V plus this V plus this V has to add up to 12. By the same reasoning, if I go around the other way, I started off at 12, I got to drop some more. So this V plus this V plus this V plus this V adds up to 12. So that's going to help me fill in some blanks. Notice I can already tell you some of the voltage drops because I know the charge on these capacitors and I know the capacitance of those capacitors. So what's going to happen is for Q1, I can find V1. V1 is going to equal Q1 divided by C1. V2 is going to equal Q2 divided by C2 because of the definition of capacitance. Wait a second. Q1 is this. C1 is 100 microfarads. So if I take that divided by 100 microfarads, I find that QR, that V1 is going to be 6.108 volts. Can't read that, I'm sorry, ran out of space. For V2, however, it'll be the same charge divided by 150 microcoulombs. It's only 4.072 volts. So I know this voltage, I know this voltage. Let's go back to my circuit though. We said this plus this plus this plus this equals 0. In other words, this plus this is 12. I know this is 6.108. This is 4 point whatever. Well, that accounts for 10 volts. They all got to add up to 12. So this must be the remaining about 2. More specifically, I can say that V3 equals 12 volts minus this and this. Excuse me. So 12 minus 6.108 minus 4.072. So it's about 1.82 volts left over. That's the 1.82 volts that was unaccounted for. It must have dropped during capacitor 3. However, if I know V3 and I know C3, I can find how much charge ended up on capacitor 3 because I can use the definition of capacitance again. Q3 should equal C3 times V3. So if I take C3, which is 200 microfarads, times V3, which is 1.82, I get 3.64 times 10 to the minus 4. You guys see where I got that? Yes.
Can you go back? I was talking, but I was still on mute. Sorry. I was saying no, I didn't see how you got it.
So I'm using the definition of capacitance. I figured out this, right, by subtracting the 2 voltages that I knew about from the 12 that I knew I had to have total, and that was what was left. Then I said that C or Q3 had equal C3 times V3. So I plugged in C3, that's 200 microfarads. I plugged in V3, that's 1.82 volts. And when I do that, I get this.
Okay.
Nifty. So now, back to my original circuit, I figured this out, this out, this out. I need to know how much charge lives on these 2 guys. However, I know that any charge that didn't go this way and end up on 3 had to go this way and end up on 4 and 5. That tells me 2 things. Thing number 1 is that because these guys are in series, they have to have the same charge. So whatever I get for C4, it's the same as whatever I got for C5. And I also know that whatever didn't go here went this way. But I know how much I had to start with. I know how much went here. Whatever's left went the other way. So to get C4 and 5, all I have to do is subtract the Q3 from Q1. So Q1 was this, Q3 is this. If I subtract this and this, that's a 4, not a 6. I was like, that can't be right. I get 2.36 coulombs, and they have to be the same. So hooray, I found all the charges. And if I wanted to, I could find V4 and V5 the same way we did before. I could take this divided by the appropriate C and get that, this divided by the appropriate C and get that. But we were looking for the charges. We found them all, so we're kind of done. So for this kind of problem, what's going to happen is once you get to step 3, the process is going to depend on the particular shape of your circuit, the particular arrangements, and you just kind of have to play it by ear and look for targets of opportunity. But you're always using a combination of 3 rules. You're using the definition of capacitance, so C for any capacitor, C equals Q over V. You're using the fact that at any intersection, the charge coming in has to equal the charge coming out. And also, for every loop, all the voltage drops have to add up to V total. And between those 3 rules, you should be able to fill in all the blanks, no matter how complicated I make the circuit. It just may take a little bit of finagling on your part. All right, so we've still got to do energy and capacitors, but I think we're going to end it for today. I think I've made you suffer enough. So I will see you guys tomorrow for lab. Isaiah, I know you haven't been to lab before. So our lab meetings for this class, when it was an on-ground class, they were starting at 8 a.m. I found that that's probably a little early for you guys. We're going to start it at 9 tomorrow. So at 9 o'clock tomorrow, feel free to show up. We'll work through our lab stuff. Otherwise, have a good day. Oh God, am I not recording? Okay, very cool.